My name is Eric van Hensbergen. I'm a fellow with ARM Research, and I'm going to be talking today about our experiences trying to use cloud-native technology on the edge. This work was done in collaboration with Alex Ferreira, Adeniyi-Jones, Edmund Grimely-Evans, Josh Miner, Mark Nutter, Louis Peña, Kanak Agarwal, and John Hermes. The project is called SMARTER, which stands for Secure, Municipal, Agricultural, Rural, and Telco Edge Research. At ARM, we foresee a world quickly moving towards 1 trillion connected devices. Managing these devices, deploying software to them, and extracting data insights from them is a daunting task. The sheer magnitude of data from 1 trillion devices requires that some form of analysis, aggregation, and filtering be performed at the edge. For the purposes of this talk, we will be limiting the scope of the edge to a gateway class of device that typically sit between the sensors, which are typically microcontroller class devices, and the rest of the internet. The gateway class devices are typically 32-bit or 64-bit systems capable of running a full Linux stack, and sometimes even have the capability to run virtualized. We envision these sorts of gateways being used in all sorts of different environments, whether they're deployed as home gateways, within the enterprise, within the telco edge, or within telco vaults. Within our project, we focus primarily on a smarter cities use case, adopting applications and requirements from the Array of Things project, which has been a deployed smarter cities project in the city of Chicago since 2014. The Array of Things project was a collaboration between the city, Argonne National Labs, Northwestern, and the University of Chicago, and is built upon their open source Waggle software stack, which predates cloud-native technologies. We looked at porting their applications and infrastructure to cloud-native options and then addressed the gaps we discovered when trying to do this on the edge. We are now collaborating with the Waggle team to incorporate these cloud-native technologies into the next release of their software and infrastructure. There are, of course, many differences between cloud and edge environments. First and foremost, security attack vectors that an edge device is subject to are far more numerous than those of a traditional cloud server sitting in a secured data center. In thinking about software and services for edge computing, we relied heavily upon the ARM platform security architecture, which defines multiple levels of security for many classes of devices. It also leverages security features which are uniquely available in embedded devices, such as secure boot, trust zone, and secure enclaves. Secondly, edge nodes in the gateway class of device are typically far more resource constrained than your typical cloud server, with less memory, storage, network, and compute power in order to stay within a certain cost range or thermal operating environment. Additionally, edge servers don't have the luxury of simply scaling out to a nearby cluster node when resources are low. This is due in part to a different connectivity model present on the edge. Edge nodes are more often behind firewalls or only have a metered cellular or low bandwidth wireless connection. They don't have the luxury of a flat high-speed network between nodes like you have in a data center. But as such, many assumptions about networking that are just fine in the cloud simply don't work on the edge. Edge nodes are also far more heterogeneous than their cloud counterparts. They contain many different types of processors, running at different speeds and different storage technologies with different peripherals. Edge nodes have physical sensors and actuators attached to them. Cloud nodes do not typically have to worry about managing cameras, gimbals, microphones, or other sensors. Cloud-native tools and development environments are rapidly becoming the standard for modern software. There are huge ecosystems, predominantly open source, which allow developers to quickly compose and scale multiple services based on pre-existing components woven together with their own value-added software. We were interested in seeing if we could bring these same benefits to the edge in embedded environments, maintaining as much of the standard APIs, tools, and methodologies so that cloud developers could quickly become edge developers. One of the core elements of cloud native is containerization technology. This allows the application and its dependencies to be packaged into a portable environment which can easily be deployed across networks. Containerized technology also provide a convenient cross-architecture development platform when developing for an ARM-based hardware on an x86 laptop, for instance. And recent extensions to the Docker container technology allow simultaneous build and packaging for multiple architectures from a single source recipe. Container technologies such as Docker also provide image repositories or registries where pre-built containers can be obtained in a secure versioned manner. We decided to structure the core of our cloud-native edge solution around Kubernetes. Kubernetes is an open source platform for managing containerized networks and services. Nodes receive instructions from a central Kubernetes server, which detail what containers to run, where to get the containers, and how to connect them to resources and networks. Containers are then pulled by the edge nodes from the registries, like the Docker Hub. For the edge, we use a subset of Kubernetes functionality due to the differences from the cloud environment. For instance, all of our applications and services are structured as daemon sets. In Kubernetes, daemon sets are provisioned to run on every node matching selection criteria. This allows new nodes that enter the system to automatically be scheduled with applications. Selection criteria is usually specified as a label or a set of labels. By using different labels, we can control which application combinations and which configurations run on each of the edge nodes. By using Kubernetes features known as taints and tolerations, we can restrict edge workloads to run on edge nodes and cloud workloads to run on cloud nodes while still using a common Kubernetes control plane. In this slide, you can see an illustration of the different edge nodes tasked with different sets of applications based on certain labels. The green nodes are only running image detection. The light blue nodes are only running the audio classifier, where the darker blue nodes are running both image detection and audio classification. These labels can be dynamically set and unset through the Kubernetes controller at any time. As mentioned before, a major difference between edge and cloud is the connectivity environment. In the cloud, Kubernetes services are free to communicate with each other no matter what node they're running on. But on the edge, with nodes behind firewalls and NATs, there is no guarantee of connectivity between any two edge nodes. As such, we structured all communication to originate at the edge and be directed to the cloud. The Kubernetes agent pulls the cloud at a configured interval for configuration updates. Data and node telemetry is pushed to the cloud rather than pulled from the edge. For debug, we set up a special communications agent which creates a reverse tunnel between the cloud and the edge, allowing direct access for developers. Not having any ingress ports on the edge node also provides security benefits, particularly for wireless edge nodes. Since we primarily either want applications to communicate with the edge node or from the edge node to the cloud, we simplified the container network interface to decouple the edge node so that it can be self-sufficient. Part of this is to use a node local embedded DNS server, which communicates with the Kubernetes agent to configure DNS names to particular application containers. And this allows the application containers to resolve internal addresses amongst each other. We also made some additional extensions, including configuring DNS masks to allow node local containers to communicate with applications running on the host. All the details of this are within the paper. Finally, management of physical sensors and actuators was something we had to add as an extension to Kubernetes for the edge. We created a new service called Smarter Device Manager, which runs as a container itself under Kubernetes. It communicates with the Kubernetes agent and informs it which devices are available and how many containers can use it simultaneously. Applications that can then specify they require access to the device in their YAML manifest, and the Smart Device Manager keeps track of ownership and access controls, including informing Docker to allow the device to appear to the application inside the container. You can see on the left-hand side of the screen an example YAML file with the section in blue highlighting the resource requirements for the application, which now include the sound device. Here's an illustration of the Smarter Stack components which make up our example, which you can find in our GitLab repository. We've tested it on a Raspberry Pi and NVIDIA Xavier AGX edge nodes, connecting to cloud services residing in an Amazon cloud instance. All applications and services are containerized. with applications communicating data over MQTT to a container running the FluentBit application, which takes care of uploading data and telemetry to the cloud, and ultimately placing it in a database for real-time visualization or later analysis. FluentBit also features support for unreliable communications, batching of data transfers, and only transmitting data when there's a sufficient difference from a previous reading. Such a configuration has been tested to thousands of edge nodes and could scale much further with proper scale-out configurations on the cloud side. We are continuing to expand the Smarter Stack functionality. There's a lot of focus on security elements, including using virtual machine-backed containers, as well as working on a formally verified secured hypervisor technology. We are also actively developing function-as-a-service layers tuned for the edge, which seem fit for many applications, as well as tools and techniques for sharing accelerators like GPUs or ML accelerators. The first prototype of the accelerator sharing, as well as the serverless features, are already present in our repositories. We're looking at methods to extend our networking technologies to allow peer-to-peer communication on the edge, and are also architecting resource and data brokering techniques to facilitate a more multi-tenant friendly edge-as-a-service model. We encourage you to read the blog entries which give more detail on the architecture and operation of the different components. We'd like to thank the Waggle team, whose applications and infrastructure we based our initial use cases on. Finally, we encourage you to have a look at our repositories and examples and try deploying your own smarter environment. We're happy to receive comments, fixes, and extensions. Thank you for your attention and enjoy the rest of the workshop. We look forward to collaborating with you all.